Log on, tune in, find out. Another good idea from Cambridge.
Okay, so we're set to have 4 interesting talks in this morning's session. The first one of which is Eric Rains from CALTECH. We'll talk about moduli spaces and elliptic difference equations.
Okay, and the good news is there are only 4 talks in this morning's session. So, yeah, actually, so I can echo Mizan's comment of yesterday afternoon. So, well, I'd first like to thank the organizers for giving me an excuse to come back to Cambridge and point out that the first time I was in Cambridge was so long ago. Well, okay, there was a Churchill College, but there was no Newton Institute, at least. So, like by a year or something. But anyway, so so I want to apologize for the abstract is somewhat misleading in that the abstract was written like a month or 2 months ago, and since then I made more progress than I thought I would. So I have a lot more to say about the last sentence of the abstract than I thought I would, and so I'm basically going to be talking about the last sentence of the abstract pretty much exclusively. So, okay, however, the title fits perfectly, the new talks, so that at least is okay. And I should mention, so some of the stuff I'm talking about is joint work with Dima Rinkin and Alexei Borodin, and others are, well, it hasn't yet been determined, but it's either joint work with a Kunkov or an effusive acknowledgement to a Kunkov, one of the two. But, okay, so I want to start by giving a little bit of a motivation for sort of why I'm interested in this particular question. So the first thing is just, and to actually bring special functions in, since I guess I'm supposed to, given this is a special functions conference, is what are some of the key properties of hypergeometric special functions? And it turns out if you look at sort of the classical things, 2f1, 8phi7, 10phi9 elliptic nonsense, and various integrals related to that, at least for univariate things, they always seem to have one thing in common. No matter how complicated you make them, you can put lots of extra parameters in. You could have an nf n-1, for instance. In each case, there's a differential equation or a difference equation or an elliptic difference equation or what have you. It satisfies some nice equation. And this equation is something you can explicitly write down the coefficients of. And there's actually a reason, in a certain sense, for why you can write these equations down. It turns out if you look at these equations, and let's take the case of the 2f1, if you look at how this differential equation behaves near the singular points, and you just need gross information about how it behaves near the singular points, the characteristic polynomial of the residues, and that's actually enough to uniquely determine the equation up to a constant change of basis. And similar things happen for the very well poised 8w7, the very well poised balanced 10w9, and all the way up to the elliptic level. You always have this property, and similarly nfn-1, things like that. You always have this rigidity property that knowing how the equation behaves near the singularities is enough to tell you the equation up to a change of basis. And so this suggests the following very natural question, which is, which in the differential equation case is essentially the topic of a whole book by Nick Katz, which is, okay, given a type of equation and some local information about the equation, when is that enough to uniquely specify the equation? And so the hope would be, for instance, that rigid elliptic difference equations would, in some way represent generalized elliptic hypergeometric functions, and so on for lower levels. It's also worth noting, so in certain cases, the theory might not have existed yet for rigidity. Like at the elliptic level, one of the motivations was just trying to actually get to the point where I could prove that the elliptic hypergeometric difference equation was rigid. But if you just sort of count parameters, you get 0 in the cases without balancing conditions and -1 in the cases with balancing conditions, but the existence of a balancing condition, it turns out, always gives you a redundancy. So you always get to add 1 when there's a balancing condition to the naive dimension. Okay. Now the other motivation is, so Arinkin and Borodin had a great deal of success dealing with constructing isomonodromy interpretations of discrete Pain-Levé equations at lower levels than the elliptic by looking at families of difference equations, but now instead of being unique difference equations specified by singular points, they were, in these cases, two-dimensional things. And they found that in certain cases that the moduli space, if you were, the algebraic variety that classified these difference equations turned out to be P2 blown up at 9 points, or P1 cross P1 blown up at 8 points, depending on how they were constructing things. And so it fit very directly into Sakai's hierarchy of the elliptic Pain-Levé equation. And so, in general, if you want to understand elliptic Pain-Levé from an isomonodromy perspective, that suggests that you want to look for a nice two-dimensional family of elliptic difference equations. And so that's going to be the subject of a paper of Arinkin, Borodin, and myself. And so in particular, you can hope to show, in general, that such a space is one of these Sakai surfaces. Okay. So in general, then, given a suitable notion of local behavior for an elliptic difference equation, it need not be the case if you make a misstep somewhere, you can easily set things up so that you don't even get a scheme, let alone a variety or anything like that. You can get some pretty nasty things popping up, these algebraic spaces, which I don't understand, or stacks if you're really unlucky. You get some really nasty things, and in stacks there isn't even a good book yet. So that's something you want to avoid. But so even just a basic question of, is this thing classified by an algebraic variety, is not necessarily immediately apparent if you set things up wrong. And so, but in any case, it turns out there is indeed a way of setting things up, and in particular, there's a way of relating this question of classifying difference equations to the sort of classification problem that algebraic geometers really like. And so half the existence statements you want, like the fact that there's actually a projective variety around that, and an open subset of that projective variety that classifies difference equations, actually end up following from things you can just sort of look in the literature and say, okay, this theorem in this paper tells me that this thing exists and is projective. So part of the idea is we want to move this into some setting where it's actually, where you don't have to do any heavy algebraic geometry lifting. Okay, so now the first question one has to think about is, what kinds of elliptic difference equations are we going to actually get? I mean, there's the sort of generic thing where you just have, okay, so, well, I like my elliptic curves to be multiplicative, so I take the multiplicative group of C mod some rank 1 subgroup generated by P inside the inner circle. But of course, if you pull that back through e to the 2 pi I, that gives you a standard, the usual form of an elliptic curve. And so, one reason I like that is because it makes the difference equations look the same as at the usual Q level, and so it makes certain limiting cases easier to think about. Yes?
What do you mean the generation on the top line? The generation as well as actually approach box for the.
Oh, so for instance, so it turns out, although I started just trying to deal with the case where everything is living on a smooth genus 1 curve, it turns out that the theory actually works in any sort of degeneration of that picture you want. So for instance, it works equally well for the Q case. Sorry, what?
So it's rational.
Yeah, if this genus 1 curve degenerates to have a node or a cusp or three components all meeting at a single point, all that sort of thing just fits just immediately into this picture because everything is being done completely algebraic geometrically, it turns out.
So singularity clashing or like Marta explained. How about
Sorry?
singularity clashing? How about?
Yeah, and there's no conditions about the singularities being distinct or anything like that.
Okay.
So when I say that this works for degenerations, I mean it works for degenerations. When you start pushing down to non-reduced curves, the issue is more a question of interpreting the answer as opposed to constructing any of these spaces. Okay, so you have this. So you have, in general, you would have an equation of the following form. So M and A are matrices because I like matrix forms for difference equations. And so if you shift Z, which is a point on this curve, by some translation on the curve, M gets multiplied by this. I guess M should really be a vector there, but anyway. And this vector gets multiplied by this matrix when you shift Z. So you could just try to classify things like that, but it turns out that you actually get a nicer classification theory, and it actually fits more naturally into things that showed up in special cases of elliptic Pain-Levé. So for instance, the hypergeometric solution of elliptic Pain-Levé, there's a way of attaching, using ideas of Forrester and Witte, there's a way of attaching an isomonitor, a lax pair to that. And if you do that, what you find is that this A matrix, well, firstly, of course, it should be essentially elliptic. So if you shift by P, well, there's some scalar, but basically it's elliptic. And secondly, you have this symmetry property here, which, if you think about it a little bit, this is just the consistency condition that you need in order for it to even be possible that there's a solution M to this equation, which is invariant under Z goes to 1 over Z. So basically what this is saying is we have this involution here, and in a certain sense we can actually solve, and if we look for meromorphic solutions, this is true, we can actually solve this equation sort of living on not our genus 1 curve, but the quotient by this involution. So certain aspects of what's going on actually live on the projective line, which, as you can imagine, is a lot simpler to deal with than a generic elliptic curve. Okay. And then the other things that, so in this particular hypergeometric case, we also then specify some discrete data. The matrix is 2 by 2, and there are 8 points where it fails to be holomorphic. And where it fails to be holomorphic, the residues at those 8 points turn out to be rank 1. And now, so to follow up on your question, of course, it's possible that those 8 points might not be distinct, but that you can deal with just by specifying the determinant of the matrix. And or equivalently, you can basically look at how this thing behaves in the local ring at that point, and basically look at the conjugacy class within the local ring, and that's enough to tell you sort of gross local invariance. And that turns out to be the right analog of the characteristic polynomial of the residue in the Fuchsian equation case. Okay, so I like, that's pretty much the end of any analysis. So there was like 2 equations worth of analysis. I like to think of things algebraically. And if you're going to be applying theorems in algebraic geometry, you first need to put it into their language. So, so what do we have? Well, A had this quasi-periodicity property, which in algebraic terms says the coefficients of A are sections of a degree 0 line bundle. And so we have a genus 1 curve over some algebraically closed field. And I'm probably the only person in the room who cares, but this does not have to be characteristic 0. And some translation of the curve. And so we have this, again, we have this formal equation here, where the only thing that's changed is the way I'm writing the addition law on the curve. And okay, A consists of rational things living in some line bundle, and it has some symmetry property. Okay. Now, in general, there's a gauge symmetry here, you can multiply this matrix M by some other matrix and get a new equation which has, in some sense, the same solution space, or canonically isomorphic solution spaces. And that symmetry turns out to be a little hard to deal with. So I'm going to ignore that. And hopefully future work can figure out sort of what the gauge symmetries are doing. So in a certain sense, this is really the last point where I'm actually thinking of this as a difference equation. But you can already sort of get a certain amount of traction on this question just by classifying matrices rather than difference equations. Because after all, if you expect most of the time there isn't going to be, unless you have apparent singularities in your matrix of your equation, you're not going to be able to gauge any of your symmetries, any of your singularities away. So if you can classify matrices, well, that's going to be basic. That's going to be at least a big piece of the classification for difference equations. So really, we're just going to look at matrices A satisfying this symmetry property, living on some line bundle, and up to a local equivalent. And we specify local conditions, which basically say, okay, well, if we want to multiply on the right by some matrix, we want to preserve symmetry, so that pretty much forces what we're multiplying on the left by. And so we multiply by a matrix like this, which is holomorphic at some pair of points. Because of our symmetry, we really need to consider pairs of points at a time. And we say, okay, we'll consider A and A prime locally equivalent at x if by using things that have poles outside x and beta minus x, we can make them equivalent. Okay. And most of the time, all this tells you is, what are the elementary divisors? If you sort of write A, if you take a sort of the natural power series ring near X and look at A as a matrix over that power series ring, what are the elementary divisors of the matrix? And that turns out to be the same as the local equivalence. At fixed points of this involution, it's more complicated, but it's indeed possible to figure out what it means. As an idea of sort of how it gets more complicated, well, when you have this symmetry property at a fixed point of the involution, well, there's an obvious way to satisfy this, make A be 1. There's another obvious way of satisfying it, make A be minus 1. And clearly you want to distinguish those two cases because their solutions have radically different singular behavior. So that's the sort of additional data that comes in for local equivalence. Now there's a nice way of turning this problem with this these annoying properties. Things are rational. We have inverses popping up. Well, it turns out there's a way of turning it into something that doesn't sort of have possible moving poles or anything like that, or that we have to contend with. And the idea is that anytime we have a matrix A with that symmetry property, with this sort of norm 1 property, we can factor it as a ratio of a matrix and its image under the involution. And, well, this is highly non-unique. Clearly, you can multiply B on the left by anything which is invariant under the involution, and we're not going to change this factor. We're not going to change A. But if you are willing to let the image of B be a vector bundle rather than just some rational vector space, then you basically get a unique factorization by insisting that B be regular. B should be a holomorphic map to this vector bundle, and the vector bundle should be as small as possible. And not only is this a canonical factorization, it's a not too difficult to compute factorization. I mean, this is something you can actually do by hand if you have, or on a computer by hand, as it were. If you have some particular matrix you want to factor like this, you can do this factorization without too much ado. Okay. And there's a bit of a caveat here. We have this degree 0 line bundle, and you need to factor it as a corresponding ratio of line bundles. And there's actually 8 different ways of doing that up to sort of invariant line bundles. So you have to make a choice there. But again, this sort of corresponds to when you're over a line bundle, there is no 1, there is no minus 1. So you have to decide which thing should play the role of 1, and then everything else sort of carries over. Okay. So, and the nice theorem here is that once you factor A in this way, this complicated question of what local equivalence means at fixed points completely goes away. And the only local equivalence just boils down to if these two matrices have the same, if these B matrices have the same elementary divisors, then the A matrices are locally equivalent and vice versa. So this is now something which there's no question of interpretation of what this actually means. So the sort of thing so the sort of information you get is, okay, at a point where B is not invertible, what's the rank of its kernel? And that's the sort of numerical data that goes into local equivalence. Okay. So really then we're going to think of this problem as classifying maps B, which are going to be injective maps from a trivial vector bundle to some non-trivial vector bundle on our curve C. And specified local behaviors at every point on our curve. Okay. So let's think about a toy example of this sort of classification problem. So if we're lucky, this map from a vector space to a vector bundle, well, we might be lucky, and this vector bundle might be trivial, so it's really just a map between two vector spaces, and we can think of this thing as a matrix after all. So let's think about the sort of thing we have there. So for instance, if we start with a rank 3 difference equation, we'd end up with a 3 by 3 matrix. And this local conditions that we're putting on, well, as I said, we're basically putting constraints on the ranks of the kernels at different points. And sort of the most generic way you can do that is at 9 distinct points, you have the rank of the matrix drops by 1, or the kernel has dimension 1. And that's, of course, equivalent to just saying, I want to say this is what the determinant of the matrix is. So we have 3 by 3 matrices, and we've said this, and we specified what we want the determinant to be on our cubic curve C0. Well, this, it turns out, you actually can construct this. You can actually construct equations for this particular moduli space. So what we have is we have 3 by 3 matrices. So that's like a 27-dimensional vector space, or a 27-dimensional space that they originally live in. And then we mod out we can multiply B by a scalar matrix on either side. And well, the scalar matrix on the left is just going to get absorbed into A anyway. The scalar matrix on the right, well, that just gets absorbed into an equivalence of A. So we can multiply on either side by a matrix. And so we have a perfect example for applying what the sort of invariant theory that algebraic geometers like. And so you can understand this moduli space by understanding the ring of invariance of GL3 cross GL3 acting on this 27-dimensional vector space. Or rather, SL3 cross SL3, because you have to kill off the scalar part. Okay, and so you do that, and well, you can compute the generating function of the dimensions of the invariant spaces as an integral over SL3 cross SL3. This is I guess it's a 4-dimensional, you can think of it as a 4-dimensional contour integral and just sort of keep expanding in residues, and it's a long calculation, but eventually what you find is that the generating function looks like the invariant ring is generated by 10 things of degree 3, 1 of degree 6, and 1 of degree 9. And in fact, well, the 10 things of degree 3 are easy to recognize. We have a 3 by 3 matrix, the coefficients of which live in a linear space. And well, we can think of that, we've been thinking of them as functions on our curve, but because they're linear, we can also think of them as functions on P2. And if we do that, then when we take the determinant, rather than getting a function on our curve, we get a cubic polynomial on P2. And a cubic polynomial has 10 coefficients, and these are clearly invariant under SL3 cross SL3. So those are our 10 invariants, our 10 cubic invariants. And then the degree 6 and degree 9 invariants you can pretty much directly construct and show that they satisfy the appropriate relations. So in particular, there's this degree 9 invariant is the square root of some polynomial in the other invariants. Okay. I don't recommend that you actually try to write these all down at home. They're pretty giant things, but I'm sweeping a lot of stuff under the rug there. But anyway, so as I said, yeah, so the 10 invariants are just the determinant viewed as a curve rather than viewed as a function on C naught. And when we specified what our determinant should be on C naught, well, we didn't quite specify a cubic curve. We specified a two-dimensional space of cubic polynomials, or rather, we specified a one-dimensional space of cubic polynomials modulo the defining equation of C naught. So our 3x3 matrix is going to have determinant living in a two-dimensional space, or geometrically, that gives us a projective line worth of cubic curves. So in particular, these 10 invariants, well, we're only allowed this two-dimensional space worth of cubic polynomials, so we're putting 8 linear constraints on these 10 cubic invariants. So what are we left with? Well, dividing our degrees by 3, we have 2 coordinates of degree 1, 1 coordinate of degree 2, 1 coordinate of degree 3, and they satisfy an equation of weighted degree 6. Well, it turns out that modulo some hideously singular exceptions, any variety of that form is a Del Pezzo surface. And so in particular, it can be written as P2 blown up at 8 points. Now, this is not giving it to us as P2 blown up at 8 points. It's actually giving it to us as the abstract surface in a canonical, or more precisely anti-canonical embedding. But at least in principle, this does tell us if we blow up a point on this degree 1 Del Pezzo surface, we'll get a Sakai surface. So it's very close to a Sakai surface. And there's another way of, and you can also think of this Del Pezzo surface, well, if you put one more linear constraint on, well, you have generators of degrees 1, 2, and 3, and a sextic equation. If you write down what the general sextic equation in variables of degree 1, 2, and 3 looks like, it's exactly the Weierstrass form of an elliptic curve. So what we actually have here is not, I mean, and this is, of course, this is true for any Del Pezzo surface of degree 1. It also, in a canonical way, is a family of elliptic curves in Weierstrass form. And the only thing you've done is you've taken the identity element, which sort of, you have this line worth of identity elements, one for each elliptic curve, and you've collapsed it, you've blown it down. And it turns out, if you actually play around with these matrices, there is in fact exactly one determinant 0 matrix, which is determinant 0 for an interesting reason, as opposed to a boring reason like having a 0 row or a 0 column or things like that. There's exactly one interesting matrix of determinant 0 up to equivalence, and that's exactly this point that corresponds to this blown down identity element. Okay. Now, at this point, you say, okay, well, we have this pencil of cubic curves, and to each one of our cubic curves, we've attached an elliptic curve. Well, there's not very many natural ways of doing that. So this immediately leads us to guess that, indeed, this elliptic curve is just going to be the Jacobian of the cubic curve. So it's almost the same curve, except that the cubic curve, well, firstly, a smooth cubic curve, you need to specify a point to identify it with an elliptic curve. And if you start to generate in the cubic curve, this Jacobian starts to generate in different ways than the cubic curve does. So there's a little bit of and so it's not quite the same as the curve downstairs, but it's pretty close. And there's actually a general fact underlying this. And basically there's a natural construction, which I'll talk about generalizations of in a bit, that if you pick a given smooth cubic curve and ask to classify the matrices having that cubic curve as determinant, they're actually in a natural way classified by line bundles of degree 0, except that you have to remove the trivial bundle. So, and this is exactly just saying you take the Jacobian and you remove the identity. And of course we have to remove the identity because that corresponds to a matrix with identically zero determinant. And that's kind of and that's not a matrix having C as determinant. And this actually generalizes, given a degree D curve, which is smooth at least, the matrices having that determinant are classified by, roughly speaking, the Jacobian of that curve. More precisely, and this matters, more precisely, it's classified by line bundles of degree D times D minus 3 over 2, which, to say in a possibly more illuminating way, this is one less than the genus of a smooth plane curve. And so in particular, this is exactly the place where the theta divisor, which is normally just a sort of family of divisors, in this particular torsor over the Jacobian, there actually is a canonical hypersurface in there which corresponds to the theta divisor, and that's exactly what needs to be removed. So again, this is a very natural object from an algebraic geometric perspective, which is good because that means it's something that algebraic geometers might actually have studied and give us useful insight into. Okay, and Beauville had this nice approach where you can basically generalize this to a certain extent by, I mean, it's difficult when your curve stops being smooth, it starts becoming much more difficult to interpret what this Picard variety ought to be, especially when your curve, your curve could be a line 3 times. I mean, because you have to think of things scheme theoretically. It's actually cut out by an equation, and if that equation is x cubed equals 0, this is really difficult to understand what this sort of sheaf, what is the analog of a line bundle on this curve and so forth. It gets really unpleasant. And it turns out it's not even quite enough to give you the full classification in that sort of case. But what you can do is, rather than think of a pair of objects, a curve in the plane and a line bundle on the curve, well, you can actually just talk about one object, which is a sheaf on the projective plane supported on that curve. In the case of a smooth curve, this is exactly the same. There's no difference there. In the case of a singular curve, you start picking up a difference, and this turns out to be the right thing. If you try to do things in terms of singular curves, even if you just pick up a node, you have to be very careful to avoid missing out on matrices in your moduli space which look like perfectly reasonable matrices that just happen to correspond to nodes on your natural Jacobian, and those are a lot harder to deal with. Okay. And, well, it turns out that this sheaf has a very nice property, especially from my perspective because I hate cohomology. Well, this sheaf has no cohomology, it turns out. So not only in the fairly traditional sense of all of its higher cohomology groups are 0, which people like, of course, it also doesn't have any global sections. Its sheaf cohomology is completely 0. It just goes away. And in fact, most of the sheaves that show up in this work end up having this property of having absolutely no cohomology. And this is a sort of property that tends to be inherited. If you have a short exact sequence and 2 things have no cohomology, the third thing has no cohomology. So it's pretty nice. Okay. And so in particular, given a matrix on P2, you can turn it into a sheaf by taking by viewing it as a map between appropriate vector bundles, neither of which has any cohomology, and taking the co-kernel, which is going to be this one-dimensional sheaf. And vice versa, given this one-dimensional sheaf, and assuming it has no cohomology, there's actually a canonical way of constructing this matrix, this map between vector bundles. And this construction is completely functorial. So sort of the natural notions of maps between matrices that correspond to things like an inclusion corresponding to a block triangular matrix map very naturally to, so a reducible matrix will map naturally to a reducible sheaf and vice versa. So there's a lot of, you pick up a lot of things like that from this equivalence here. Okay, and similarly, if you fix a cubic curve in the plane, and want to talk about matrices on that cubic curve with linear coefficients, well, you just interpret those linear coefficients as linear polynomials on P2, and that again is going to be completely an equivalence of those categories. So the upshot is matrices on a cubic curve with specified determinant are classified by matrices on a cubic curve with no constraint on the determinant are classified by one-dimensional sheaves on P2. Okay, and there's a similar construction where if given a sheaf on, say, P1 cross P1, or more generally a Hertzberg surface that has no cohomology, then you can construct one of these symmetric matrices A and vice versa. And this curve C that you end up getting has a nice interpretation as A and, well, for given a point on P1, there's two matrices over it, because of course you have x and beta minus x both mapped to the same point. But those matrices are inverse of each other, so they have the same eigenvectors. And so if you look at the set of all eigenvectors of all matrices A, this naturally has a degree n map to P1, and this turns out to be this curve C. And in fact, the map tells it is enough to specify this line bundle on C when things are smooth. And so that's most of what you need to construct this sheaf on the Hertzberg surface. So I've heard people talk about spectral curves around here. I don't know whether that's the sort of thing they mean, but at the very least, this seems deserving of the name. So, okay, now, so far, of course, all we're doing is we're classifying all matrices of a certain, and we really want to say, here are some, we want to specify these local conditions. So how to deal with that? Well, it turns out this vanishing property for the cohomology is extremely robust. I already mentioned exact sequences, but it also works nicely under pullbacks by birational maps and push forwards. So in particular, this, at least for one-dimensional sheaves without cohomology, pushing forward under any projective morphism, I think proper is enough, but anyway, we don't need that. Pushing forward under any projective morphism gives you again a one-dimensional sheaf with no cohomology. Pulling back under a birational morphism, so in particular, if you blow up a point and pull back through blowing up a point, that also preserves this vanishing cohomology property. And furthermore, you know, it has this sort of nice property you want that if you lift it to a blow up of your surface and push it back down, you don't go anywhere. You get the same thing you started with. Okay. Now, pushing forward, there's actually plenty of sheaves that just go away when you push forward. Because basically any sheaf that's just supported on one of the exceptional curves, if you blow up a point, you have this nice line living above your point. And any sheaf supported just on that line is going to go away when you push forward. At least if it has vanishing cohomology. So there's all sorts of stuff you can do to your sheaf without changing its push forward. But it turns out that among all the things that have that same push forward, there's a canonical choice, which is minimal in a certain sense. Okay, and in terms of matrices, if we start with a sheaf that came from a matrix, blow up a point and take the minimal representative upstairs. Well, it turns out that all we're doing is we're basically when you do this blow up process, you get a certain sheaf. There's a subsheaf or maybe a quotient, I forget which, but there's a piece of your sheaf which is supported just on the exceptional line, and it turns out to be basically essentially just a vector bundle on that exceptional line, and the rank of that vector bundle is the dimension of the kernel of your matrix at that point. And it turns out to get the minimal thing, you're supposed to remove that piece. But what that ends up telling you is that when you take this canonical representative upstairs, you can read off this one portion of the local condition, the rank at that point, by knowing the Chern class of the minimal representative. Whatever a Chern class is, you don't, to a certain extent, you don't need to know. You just basically say, well, it satisfies a bunch of formulas, and it's enough to let you compute things if you know the Chern class. And more importantly, the Chern class is the sort of thing that algebraic geometers like to specify when they're defining moduli spaces. They often talk about moduli spaces of sheaves with specified Chern class. So the fact that we're getting information about the Chern class is really nice for being lazy and resorting to existing literature. Okay, and more generally, in these degenerate cases where you have more complicated singularity behavior, well, what you end up having to do there to resolve the singularities is you end up having to blow up a point on that exceptional line. And it turns out that that if you sort of keep blowing points up until you've gotten rid of all the singularity, the ranks you get at each step are exactly the information you need for these local conditions. So the upshot is that given your local conditions, there's a natural way, there's an associated blowup of P2 or P1 cross P1, depending on which of these types of matrices you're looking at. There's a natural blowup of your starting rational surface and a Chern class on that surface such that the elliptic matrices with the specified local invariance up to changes of basis are naturally identified with sheaves on that blown up rational surface with this specified Chern class. And so immediately we can say, okay, well, the moduli space of sheaves extends to a projective variety. And people have constructed this sort of projective moduli space. So this already tells us something that we, sort of, to a certain extent, we could already have told that this was quasi-projective just because we sort of had enough equations floating around, at least in the P2 case where the things are just matrices. But what this tells us is that there's not just that it can be extended to a projective variety, but that there's a natural way of extending it to a projective variety. And this is nice to have, because otherwise there's a whole sort of question of what do you do at the edges if you want to make things projective. Okay. And there's also something kind of interesting that pops up because of this equivalence here. So we get this open subset of this moduli space of sheaves. And this open subset that we get doesn't care about where we started. It's just, you can define this open subset completely just from the rational surface in the Chern class. So in particular, we can start with a matrix on P2, resolve, say on a cubic curve in P2, resolve the singularities, and then take any other way of mapping that surface down to P2 or P1 cross P1 or our favorite nice rational surface, push it down, and turn it into a matrix. Now, when you do that, this can completely move the local conditions around, it turns out. So for instance, the rank of the matrix you get, you can start with a 3x3 matrix on P2, blow up, push down, and end up with a 2x2 matrix on P1 cross P1, and things like that. So there's a whole whole slew of transformations along these lines that can go around. And as a very special case, you can start with a 2x2 matrix on P1 cross P1 with 8 singular points, resolve the singularities, push it back down to a different P1 cross P1, and get another matrix with another 2x2 matrix with 8 singular points. Or even more simply, start with one of these symmetric difference equations, turn it into a sheaf on P1 cross P1, and observe that, and notice that the construction of this sheaf on P1 cross P1 treats the two factors differently. So we can swap the two P1s and get a different difference equation. And at least experimentally, this is the same as, this corresponds to the same integral operator that Simon was using on Monday in this BC1 case that he was talking about, which in a special functions context was considered by Spiridonov and Varnar as a certain analog of as a sort of elliptic analog of the Fourier transform. It's a certain involution. And so it turns out that, so already this is giving us something new. And in fact, another motivation for wanting to understand this way of doing things is trying to deal with this transformation in such a way that I could actually prove things about the transformation as opposed to just conjecture things about the transformation. So for instance here, if you start blowing things up and looking at moving around in the space of different maps to P1 cross P1, you find that this transformation satisfies certain braid relations and things like that are completely obvious in terms of rational surfaces and completely mystifying in terms of this integral operator. Or sorry, in terms of algebraic manipulations with the integral operator. Okay. So, okay. Now, one thing that I want to mention, just because it's so nice for us, is in this theory of general moduli spaces, there's choices you have to make in order to actually construct this projective completion. And I told you it was actually a natural compactification. Well, it turns out that all the choices, the choice you have to make, this sort of embedding of your ambient surface in projective space, any choice you make gives you exactly the same moduli space in this very special case of things with Euler characteristic 0. So it's really nice. Other things that happen is there's a natural alternating pairing on the tangent space, at least at the sort of obvious smooth locus. And we had the, if your family has smooth curve, if your family of supports has smooth curves in it, then if you look at a generic smooth curve there, then the fiber of that smooth curve is exactly this pic G minus 1. And that actually, the restriction of this pairing to that fiber turns out to be trivial. And if you count dimensions, the dimension is 2G, so this is actually a Lagrangian fibration of this probably symplectic. The form we don't yet know it's closed because the lazy algebraic geometers haven't proved it's closed yet. But it's basically modulo that little issue. This is the symplectic variety, and we have this nice Lagrangian fibration by essentially abelian varieties. Now, this is actually slightly unfortunate because if we'd only managed to get degree G instead of degree G minus 1, this variety would actually, this moduli space would actually be rational because, well, a divisor of degree G is essentially the same as G points without ordering. And G points on a curve determine G points on the rational surface. And these curves live in a G plus 1 dimensional linear space. So G points on the surface give you a unique curve and a unique divisor on the curve. So there's actually a natural birational map between the slightly twisted version of this moduli space where we have pic G instead of pic G minus 1 and the G symmetric power of our rational surface. And that's automatically rational. Okay, but we actually get saved a little bit. So under certain conditions, there are degree 1 line bundles. We actually get a family of degree 1 line bundles on our curve, and that lets us translate back down to G minus 1. So under a certain primitivity condition, you actually do get rationality here. Okay. And similarly, there's a bunch of degree 0 line bundles. There's a bunch of families of degree 0 line bundles on our family of curves. And you can translate by any one of those. So you actually get a pretty large lattice acting on this moduli space. In addition to this large Coxeter group acting on the different ways of turning it into a matrix. In the case of elliptic Pain-Levé, the lattice turns out to be a subgroup of the Coxeter group, but this is not true in general, as far as I can tell. Okay, and so in some sense, this is basically dealing with isospectral as opposed to isomonodromy, which is unfortunate. And also from the vague things I've heard about QRT, this seems to be an analog of QRT in some sense. Okay, so now to get back to the motivation in the short time I have left, so for the rigid case, indeed this theory lets you completely classify rigid elliptic difference equations. And it turns out that, well, there's this natural Coxeter group that pops up, just like in Sakai's picture. And the rigid local conditions precisely correspond to, well, sorry, this is actually a lie, but basically, it's basically correspond to roots of this root system. And more geometrically, they correspond to -2 curves on your rational surface. So this question of classifying rigid difference equations boils down to a completely geometric thing of classifying curves of a particular kind on this surface. And again, I should say, turning one of these -2 curves, well, given a collection of local conditions, finding the -2 curve and turning it into a matrix are both very easy, but completely algorithmic things you can do. Okay, and then finally, the two-dimensional case. So in general, there's a formula for the dimension, and there's this very nice condition that the self-intersection is 0 corresponding to dimension 2. So if you have this dimension 2 condition and a technical condition about having at least one smooth curve that's as a possible support, then the moduli space is always an elliptic surface. And under certain not too hard to satisfy conditions, in particular it's always true in characteristic 0, you get a rational elliptic surface. So in particular, this moduli space in the two-dimensional case is always non-uniquely P2 blown up at 9 points, which are the base point of a pencil of cubic curves, the base points of a pencil of cubic curves. So it's not quite the same as the Sakai thing, but it mainly has to do with the fact that this is isospectral as opposed to isomonodermy. Okay, and so probably there's some indications that there's a way to generalize this to this same picture to isomonodermy in a reasonably seamless way, but I'll close by making the scary comment that it looks like it involves sheaves on non-commutative surfaces, and so it's going to take a bit longer because that theory doesn't exist yet, so the moduli space theory. So anyway, but this is where things are.
Well, the elliptic hypergeometric series which implicitly appeared here, are there non-terminating series, and are there any problems with convergence?
Well, there's the integrals.
Yeah, but can you overcome this somehow? Does it still make
Well,
sense?
I mean, if you write down the difference equation and try to solve it, you're just immediately led to the integral. I mean, so the point is there's even if you look at the higher order elliptic difference equations, there's always a basis of solution in terms of integrals, which in certain cases may degenerate to sums. But the finite sums are always degenerations of the integral case, at least.
So formally one could consider on the series level just infinite series.
One could formally, and I mean, probably there are things one could say where if you took a formal series like that, it would still satisfy the same formal difference equation, maybe. But I mean, to really get these difference equations, you always, I mean, well, in the order 1 case, typically you need to use the transformation to actually construct the full difference equation. And similarly, at higher levels, you need to use analogous ideas to get the full difference equation. So you really do need to use more structure than is just immediately apparent from, say, the term of the sum or the integrand of the integral before you can get the difference equation. So it's not quite clear. I mean, I think there is a general philosophy that has a certain amount of support from some other ways of looking at this theory, that any hypergeometric sum or integral, even if you have a whole nested sequence like a fourfold sum or what have you, anything like that should satisfy difference equations. Whether or not they're rigid can depend on the specific equation. Like there's a difference equation satisfied by the elliptic Selberg integral or the Selberg integral, or the differential equation satisfied by the Selberg integral. Those are not rigid, but, or at least not without putting extra constraints on which we don't understand.
Is there a way to get a Lax pair for a Sakai's equation of this formalism?
Well, so as I said, this is at the moment this is basically Q. In some sense, this is the Q equals 1 case that this ends up dealing with. But it should be the case that if one does the obvious sort of isomonotony transformations of this difference equation, then that should end up giving you a birational map between moduli spaces. And so, because to a certain extent, it's pretty much it's well defined on generic matrices. So the fact that it's well defined on generic matrices means it's going to be well defined on generic sheaves. Whether you can write it down in terms of sheaves is another question. So at least in principle, once you have these moduli spaces, the Lax pair exists as certain involving certain modifications of these vector bundles, a la Arinkin and Borodin. But it's only in small cases like the actual elliptic Pan-Lavie case where the Lax pair, where we've really managed to write down the Lax pair in any sort of way. I mean, if you look in part 1 of this series, so my solo paper, an isomonotony interpretation of the elliptic Pan-Lavie equation, there's at least a Lax pair for the hypergeometric case in there, and in general you have a Lax pair of the same sort of structure. It's just writing it down explicitly is, it requires, among other things, the ability to work with these complicated equations without making mistakes, and I don't have that ability. But you'll notice there weren't any explicit equations here. That's partly because I wanted to make sure I was actually telling the truth. But basically, in general, there's sort of, in that case at least, the atomic operations are relatively simple, and you can always describe them by putting the matrix into an appropriate basis, and then multiplying and dividing the rows and columns by appropriate sort of degree 1 theta functions, and then that gives you a difference equation of the shifted singularities with shifted singularities. So that's basically where that picture is. So there's at least a description of how to move the singularities around via these birational maps explicitly in terms of matrices at the Sakai level. And presumably the same ideas. But the main obstruction at higher levels is that the atomic operations can be a lot more complicated. Because at least this classification, you have this matrix which even in the Hertzberg surface case is mapping from a vector space to a vector bundle. And these modifications want to turn this vector space, which is into a non-trivial vector bundle. And so you have to do combinations of these operations that actually have a chance of giving you a trivial vector bundle in the end. And those can be pretty complicated in higher rank cases. Because like the sum of the ranks of the singularities you're using to modify has to be a multiple of the rank of the equation. So that's an annoyingly non-trivial condition. So I think to really get the isomonotony, the Lax pair perspective, either one needs to do this non-commutative algebra approach, which I agree is scary, or you have to, or you need to sort of step back and just sort of focus on, okay, suppose we fix our curve that we're supported on, or we fix some piece of the moduli space, which is still general enough to deal with, and look at the modifications there, or somehow generalize this picture so that both sides could be vector bundles. So that's sort of the thing that's missing to get the modifications popping out. Because if you can do both sides being vector bundles, then the elementary operation is just modifying at one singular point, because you don't care that it leaves you at a non-trivial vector bundle because you started at a non-trivial vector bundle. So that's basically where things are.
So can you describe what is the simplest non-trivial rigid example by given rank and set of local
Okay, so these, let me start by the simplest ones.
Yeah.
So the simplest ones, rank 1 equations, always rigid. Okay.
What about
And then in general, it's a theorem that you can always get from to any rigid equation starting from sort of the trivial rank 1 equation, m of q plus e equals m of z, by these transformations, but this analog of middle convolution, yes. So the simplest non-trivial case are, let's do on P1 cross P1, 2 by 2 matrices with the symmetry property and 6 singular points, 6 sort of generic singular points. Or if you want to, in terms of matrices on P2, it's 2 by 2 matrices over P2 with specified determinant.
For instance, we expect that as an operator of respawn should be all in the rigid case.
No. So because this relativistic Coin equation is actually a family of equations.
Yeah.
It's a one-parameter family because you have this eigenvalue. So it can't be. But if you look at the singular points, the singularities don't actually move in this equation. Sort of if you kill off the apparent singularities, the non-apparent singularities don't actually move. Don't actually depend on the eigenvalue. So this actually is a one-parameter family of difference equations, and indeed it turns out that it's basically it's a line in the appropriate Sakai surface. Unfortunately, it's exactly the line that gets removed here.
Yeah, I'm talking about the rigid case.
Well, no.
DC on Rasmus operators, for instance. The rigid.
Well, but this is the 8-parameter one, right?
Yeah.
Yeah. Well, then no, it's not rigid.
Not rigid.
Because it's an eigenvalue equation. If you have an eigenvalue that you can move, it can't be rigid. Unless somehow the eigenvalue actually gives you a completely equivalent equation, which would be kind of surprising. And if you have an eigenvalue,
Like the accessory parameter.
it gives you a parameter, basically, yeah. And the rigid case is exactly the cases where there are no parameters.
So specifying the eigenvalue, it becomes.
If you specify an eigenvalue, it may become. So if there's a value of the eigenvalue where two of your singularities turn out to be apparent,
Yeah.
then that would end up being rigid. Okay. But anyway, the other way of describing the simplest rigid case, it's the difference equation satisfied by the 12v11, or the corresponding integral.
So let's thank our speaker again.